I'm here today representing SAN Technologies. Before I tell you a bit about SAN Technologies, I just want to say thank you to NVIDIA and AWS, giving us the platform and tools to develop these solutions. And today we're going to take you through some of the solutions that we utilize these services for. Before jumping into a demo, I just wanted to give a brief intro of SAN Technologies. So we help CTOs, governments solve their core strategic challenges using AI. Some of our core propositions are around using machine learning and physics-based models to help companies deploy CapEx more efficiently. So being able to predict demand and revenue expansion or accurately estimate cost across wireless, fiber, fixed wireless access, or a range of telecommunication technologies. The other solution or capability, the one that we're going to demo for you today is our RAN digital twin. This digital twin essentially helps operators to optimize their existing network, redistribute capacity in order to find hidden markets to improve their revenue potential using their existing asset base without reducing any quality of service parameters or KPIs. So I'm going to hand over to Devin to give a demo of that RAN digital twin.
Thank you, Andrew. So diving into the RAN digital twin here. So for us to model the 3D signal landscape, we require a set of inputs that go into our radio frequency propagation engine. The first one is called the digital terrain model, detailing the height of the ground at any point across the grid. The second is our digital surface model, detailing the height of the ground and the total surface, so it could be a building or a tree. And then a clutter classification model, so at each point in the grid, is it a tree, a road, or a water body, and so on. And finally, we take in all the existing site locations together with their configurations and antenna parameters so that we can model the signal landscape. Combining all of these together, we can then produce the RFP output. And here we have it for the area of Cape Town, South Africa, with a strong signal in blue and weaker signal in orange. And you can see strong signal propagating out towards the harbor area of the V&A waterfront. Now, this is the supply layer for the RAN network. Now, supply by itself is not powerful enough. We obviously want to match that with demand, knowing where the users are during the day and during the night. So here we have two demand patterns, one at 12 o'clock. You can see everyone in the industrial areas during the business day. And here we want to have one at 6 o'clock, showing people moving out towards the sort of coastal suburban area of Fresno. We then have an AI model that's trained on the network to make tweaks to the parameters to optimize towards a set of business KPIs. Now, this could be an improvement in RSRP or an improvement in SIN-R. It could be a reduction in energy and so on. For each step, the AI model will make an adjustment and then calculate how much it has improved the network. Over thousands of steps, thousands of simulations, the AI model will eventually converge to an optimal set of configuration parameters. Once the AI model has converged, it'll then provide these parameters to the operator so that he can make these changes. So you can see here, the default azimuth of 164 is then suggested to be 184. So this takes in all of the antennas across the network and finds the optimal set of configurations to maximize the KPIs provided by the operator. Diving into some high-level metrics here. So we have the demand layer that was optimized against 509 transmitters, and we see an improvement in 5.4 decibels in high demand areas. We have an improvement in 17.82% in customer satisfaction, and we have the relative priority of sites here ranked from red being the lower priority to green being the highest priority. Thank you. That was our RAN digital twin demo.